So there are some field theories that can be renormalized and sense made out of the infinities, and others which cannot even be renormalized. Quantum electrodynamics turns out to be renormalized. And when I say you get an accuracy of 9 places in decimal, these are people who have in effect gotten an answer that's infinite, subtracted out of it an infinity, not randomly, arbitrarily, but in a very clear way. The remaining answer is 0.0000, that exists. It's an intellectual achievement really beyond belief. People who are involved in it are people like Schwinger, Feynman, Bethe, Dyson, Tokunaga, Weisskopf, no bunch of them. Anyway, apart from all these things of renormalizability and so on, infinities, these theories like electrodynamics, quantum electrodynamics, combine relativity with quantum mechanics. It all works very well. It explains for you electroweak theory, all the angles theories, and Higgs fields, everything is explained by field theories, appropriately complicated field theories. The problem comes when you try to incorporate gravity into the scheme. Loosely speaking, because the analog of this matrix element in gravity is stronger at large k, there is k dependence, loosely speaking, k is the intermediate state, is stronger than in electrodynamics or Yang-Mills theory. And so the convergence of that series, the relativistic analog of the simple series, I wrote down, that series diverges so badly that you can't even talk your way out of it. It can't be renormalized. And I'm really using the words, I'm not really showing you this. So, incorporating gravity, you have a quantum mechanical theory of, say, particles interacting with gravity, which is the oldest thing we know in science, physics. That cannot be done quantum, at least in field theory. So this was a sad situation. Making quantum theory consistent with general relativity proved to be not possible in quantum field theory. It's been a big lacuna in physics of quantum theory, where everything except gravity is to be clear. So as a result of this came string theory, one of the consequences of this, and if quantum field theory is difficult to explain, string theory is even more so. I won't even attempt it, that's not my field. But if field theory deals with fields which are the coordinates are the value of the field at every point, in string theory the fields are defined over lines, closed curves, or open curves over strings, which themselves float in space and time. It's a much more complicated system. But the principles of quantum mechanics are the same, and better be the same. But what it does, the string theory does is, it is able to accommodate, it's a more complicated quantum system, it's able to accommodate not only varying number of particles, varying number of species, but the same string theory and a whole tower of particle species. So the current candidates have all things, Yang-Mills fields, electromagnetic fields, quarks, leptons, the works, you can build it into it. Most importantly, it includes gravity as one of the particles. And the way the infinity problem of gravity does not occur in string theory, requires a little more experience with where these infinities come from. They come from when particles come very near each other. But here, because the fields are distributed over a string, that problem is less acute. If you don't understand this, I don't blame you. But roughly speaking, that is what happens. So it turns out that the infinity problem that we encounter in field theory, gravity doesn't happen. In string theory, a complete string theory is yet to happen, which will really explain all the physics of real particles. But there's very little doubt that when it comes, it will, the principles are all there. When it comes, it will incorporate gravity also into a quantum theory. And incorporating gravity is the same thing as being general relativistically correct. Because gravity, in order to incorporate gravity, you have to use general relativistic invariants, and that is done in these theories. So when that happens, most of the marriage is over, but the last part, with the piece between the quantum principles and relativistic principles, when that happens, and that may happen soon. Sorry, I took a very long.
Thank you, sir, for this interesting talk. So, if you have any questions,
I mean, so feel free to walk out, and those who want to ask questions, please.
Yeah, there is relation E squared by S bar C. That's 1 by 137.
Sorry.
That number 1 by 137. That is to be perfect. So that is to be perfect by. And because again, I will say that.
Wait, that number makes perfect marriage, and what's next?
I mean, quantum and this theory.
The theory is the marriage. That is just one consequence of it.
But if you go in ugly inverse,
That I cannot tell. I really do not know. You have never been there, so I just don't know what the value is.
that somebody either given 451
No, you have to be careful. The number does not mean anything. Calculating d square by h bar c upper value in a non-relativistic quantum mechanics is still the speed of the electron. So that number doesn't say anything. It's just an indication of the strength of electromagnetic force. Similarly, there is a number indicating the gravitational force, which is what you're talking about. The fact that those numbers exist doesn't mean the marriage is taking place. You need a single formulation which is consistent with all the rules of quantum mechanics and all the rules of relativity. And in the early universe, you don't need that.
But I believe actually gravity is missing from that direction. If we can put gravity also, we can